Hi, everybody. I'm Avery. Welcome to SREcon Conversations, or as I like to call it, SREcon. I'm trying to make it happen. I don't know if it's going to happen. Anyway, I'm here to talk to you about networks, specifically unreasonably sized networks. I know everybody here is interested in SRE, so when you hear unreasonably sized, you're probably thinking very large. But what I mean by unreasonably is that the size doesn't match the architecture. And I'll get into exactly what that means. But like small networks can be unreasonable if you design them wrong, so can large networks. Now, when we're talking about networks, I want to talk about both human relationships, which I'm bad at, and computer networks, which I think I'm pretty good at. The two things have a lot in common, it turns out. And I think we can learn a lot about one by studying the other. So I'm going to go back and forth a little bit between human relationships and computer networks. So let's talk about network sizes. There are two laws that probably most of you have heard of before, but maybe not seen side by side. First one is Metcalfes Law. Bob Metcalfe was one of the inventors of Ethernet. And he actually didn't originally say this in so many words, but it was written down by somebody else who attributed it to him and called it Metcalfes Law. The effect of a telecommunications network is proportional to the square of the number of connected users of the system, basically order n squared. So that, often when people paraphrase that, they will, instead of the word effect, they'll say the value of a telecommunications network. So this was originally about things like telephone networks and fax machines. The value of having a fax machine was very low when you were the only person in the world with a fax machine. When everybody else in the world has a fax machine, the value of your fax machine is a lot higher. Now, Brooks's law is almost the same thing. This is the guy who wrote the Mythical Man Month. Communication overhead increases as the number of people increases. Due to combinatorial explosion, the number of different communication channels increases rapidly with the number of people. So a lot of people go and simplify that and say order n squared again. If you're on a team with 5 people, you've got 4 different communication channels. 5 factorial communication channels. If you're on a team with 10 people, you have 10 factorial communication channels. It starts to get out of control. So we've got a picture of that there in the middle. This is what the communication channels look like on a 10-person network where everybody is connected to everybody else. That's pretty complicated. And what Brooks is saying is that teams get harder and harder to manage the more communication channels you have. Now, he didn't actually say n squared because I think he realizes that as networks get bigger, you don't have a connection between everybody and everybody else. And I'm going to talk about that because that's one of the main points of this talk. Metcalfe's law is kind of similar. Not everybody in the world is going to be faxing everybody else in the world. The value of the network is how many people you have the ability to fax, but it doesn't necessarily mean you need to fax every single person. So the value grows slower than n squared. Just like in Brooks's law, the cost also grows slower than n squared, but it's faster than linearly. While I was looking those up, Wikipedia pointed me at more laws named after people who didn't actually say the thing that they're attributed to. Linus's law was a really interesting one that I think is also relevant here. So the person who named Linus's law, Eric S. Raymond, said, given enough eyeballs, all bugs are shallow. And what he meant by that is, in reference to open source, when you have a lot of people looking at the source code for something, it's easier to find the bugs in that something. The more people who look at it, the more bugs they will find. And so this is supposed to be one of the values of open source. This has been a little bit disproven shortly after it was said. So there's been various different studies where people found like, okay, there is some value in somebody reading your code, but the value decreases rapidly the more people read it. So you get some value from the first code reviewer, you get a little bit less from the next code reviewer. Beyond about 4 code reviewers, you have significant diminishing returns. That said, in practice, Linus's law actually comes out, and I consider it to be sort of like actually not as optimistic as the original statement. The negative version of Linus's law, which is the sort of real world version, is Google's, here's a quote from a study. Google's popular products had a 27% higher bug fix rate than Google's less popular projects. This is an indication of increased bug detection efficiency in popular projects. So what they're saying here is they studied what percentage of commits in a Git repository are bug fixes versus new features. And they found that in the more popular projects, they had a considerably higher rate of fixing bugs versus new features. And the reason for that in their opinion, is that the more users you have, the more bugs they find at some certain rate. Now, it's certainly not, double the number of users get double the number of bugs, but you do get more bugs as you increase the number of users. And I think we've all kind of seen that. I certainly personally have a rule of thumb that says if your project doubles in size, you will reach a new level of bug finding. You'll find a new type of bug that you couldn't even see before, and that calls for a new level of quality control. In this particular case, there could be a correlation causation problem. These people did the study where they correlated high bug fix rates with popular projects, but it's quite possible that the product was actually more popular because people fixed more bugs. Nevertheless, I think we can all sort of see that there's a qualitative difference. The more users you have, the more trouble you're going to get. And so I'm going to summarize that into that law, something I put down at the bottom here, which I call the law of the panopticon. The more connected a network gets, the more criticism everybody gets. Twitter is a great example of that, right? When you post something on Twitter, you're much more likely to get criticized or some jerk is going to come after you than if you post something, to your friend on iMessage. Similarly, if you make open source code and you do something stupid, other people will see the stupid thing that you did versus proprietary code where only your coworkers will see the stupid thing that you did, right? The more connected the network is, human networks as well as communications networks, the more people will see your mistakes, the more people that will attack you. And that leads us to someone named Dunbar and his various coworkers who studied this sort of an effect of network sizes in biology and in humans in particular. So they started off by actually trying to estimate the natural group sizes for different species of animals, including humans at the end. So they took various types of animals, figured out what their group sizes were based on their brain size, and then extrapolated that to the brain size of humans and determined that the optimal group size for humans is somewhere around like 100 to 250 people, which nowadays people generally tend to summarize as around 150, although the original study didn't come up with anything nearly that precise. 150 is sort of the number of people you can personally remember as people. Now, obviously, some people have better memories than others for individuals. I have a worse memory than others, but 150 is roughly the number that works. And people find all kinds of interesting transition points as soon as group sizes grow above 150. So when I was proposing this talk, somebody sent me a link to a book called Liars and Outliers by Bruce Schneier, who's a security researcher. I've read through it. It's actually a pretty good book, but I found some great quotes about it that hopefully you can relate to. One of them is companies smaller than 150 don't bother with name badges. And I think that matches my experience in my career. Companies that have less than 150 people, you kind of recognize everyone who should be in the office, and so you don't need a name badge to let people into the office. Once you grow beyond that size, things start changing. Another quote, which is even more interesting about networks, in small companies, Alice and Bob, because he's a security researcher, everybody's always named Alice and Bob. Alice and Bob handle accounting. In larger companies, it's the accounting department, and maybe you know somebody there personally. So that's a lot of stuff in one statement. In a smaller company, everybody knows everybody, so you know exactly who handles accounting, and it's Alice and Bob. In the larger company, you don't know everybody that handles accounting. The accounting team probably knows everybody in the accounting team. And your team probably knows everybody in your team. And maybe somebody in your team knows somebody in the accounting team, right? But it's very different from a fully interconnected network. Let's talk a little bit more about Dunbar's numbers. 150 is the one everybody knows, but as the research goes on, people found that there are different layers of hierarchy, roughly in a 3 to 5 times multiple from each other. And 150 is the magic transition point, but there's a bunch of other entries along the way. And I want to go through some of them. Dunbar was an anthropologist, so he studied this in various different civilizations. I don't know that much about anthropology, and it seems like something can get me into trouble. So I'm going to start with Western civilization instead. And these sort of things are repeated all over different kinds of societies. Western society just happens to be the one I know the most about. So a unit of 1, of course, is me, 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 me. That means no network at all, basically. A unit of 3 to 5 is what we call a household or a single family unit. Many of us grew up in a household that size. People can all eat at the same dinner table. intimately every single person in that group. As you get a little bit bigger, you have something called a homestead, 10 to 15 people. My mom grew up on a farm. Her family was about that size. Farms typically need more than 3 to 5 people to operate, but not many more than 10 to 15. Smaller farms, obviously. Those people, it's a little bit tricky to get everybody sitting at the dinner table all at the same time, but you can have a family get together where everybody is all in the same place at the same time. Similarly, in the less rural, more urban type of world, if you live in a suburb, you might get your neighborhood together for a neighborhood meeting. That would be roughly 10 to 15 people. You can all show up at somebody's house and have a meeting. It might be a little bit of a mess of a meeting, but you can actually do it. As you get bigger, there's the concept of a hamlet. I'll skip over that. And then there's the village at around 150. I looked up all these terms in Wikipedia, by the way. So these are like relatively standard sizes. Obviously, it's not exactly 50 and it's not exactly 150, but a village is in the very low hundreds. And the village is the largest unit you can get to before things start getting complicated, right? Now, interestingly, when you jump past the village to the next level around 500, I couldn't find a term in Wikipedia for what that's called. And I think it might be because there just aren't very many of them. I think a village that got that big would be dysfunctional. And the next level up would be just too much overhead. So I suspect maybe what happens is you just get, a village ends up being a few villages. And then eventually, once you've got enough villages, it gets too confusing and you have to put together a combination called a township. And I grew up in a township. They were, they're pretty small, but they have a little bit of government. As you move up, there's more and more levels of government, right? Towns, boroughs, cities. And then, there wasn't enough room on this slide, so I started jamming them together, but you get metropolises, and then from there you get provinces and then nations and federations and so on. At each level, the government you need gets more complicated. But that dark line underneath village is the difference between when you have a government and when you don't have a government. If you have a village, you don't really need a government. People can generally get together and make a decision on their own. Often people bring up the fact that it turns out historically for thousands of years, militaries have been organized around similar levels. I don't know very much about the military at all, except that, a single person is called a soldier. I didn't know the term fire team until last year when I downloaded Destiny 2, the video game, which uses the word fire team a lot, but apparently it's been used for hundreds of years. As you get bigger and bigger, you get more and more complicated. One interesting thing is that a squad is the largest unit that tends to be run by a non-commissioned officer. As soon as you get into a platoon, suddenly you've got an officer who is specialized in leadership. And a company, I like the word company here. It turns out one of the earliest uses of the word company was for the military, just because it shows up in so many different places in English, right? Company is somebody you have to keep you company. A company is a group of people who work together as a business, but you often don't find yourself using the word company for really large businesses, right? We use terms like corporation or enterprise. Company is as large as it gets, but it's also as large as the largest group in the military where everybody can know each other. After that, you have to start having very formal arrangements or nothing can get done. And then the largest I could find for a military is around 50,000 as a military corps. As you get larger than that, people start writing Wikipedia articles about multiple armies getting together in World War I and so on. And that obviously can be very complicated to operate. Speaking of corporations a little bit, I want to go through the different sizes of corporation because it turns out they match up with these things as well, right? A sole proprietorship is one person, a partnership is a small number of people, a seed stage startup is around 10 or 15 people, Series A startup gets up to around 50, and the Series B startup gets up to around 150. Assuming you're building tech startups, of course. After 150, things are kind of different, right? You start scaling around, the 50 to 150 point because you found your business model and you're starting to build structures, right? And you want to be able to build things scalably, and you need to put in vice presidents and directors and executives and so on. You've crossed over this line, and next thing you know, you're a small or medium-sized business, right? So at 500 or so, that's kind of the definition that a lot of people use for a small business. 3 to 5K is about a medium-sized business. Once you get bigger than that, people start calling you an enterprise. If you get even bigger, you're probably a large enterprise. Once you get into the 150K range, there's only a few of those, but I use the term mega corporation to describe them. And then once you get into the sort of millions region, like what happens when you put a whole bunch of megacorps together? Well, you get a military industrial complex. Interestingly, again, I decided to try to map these numbers onto IPv4 subnet prefixes. And interesting, I guess it's not that surprising, but if you have a multiplier of 3 to 5 for each step, that's about 4. And so it turns out that IPv4, 2 bits of IPv4 subnet maps pretty nicely onto each of these steps. So, as, of course, an individual person is a /32. I found it very entertaining and coincidental that the largest size of a team where you can really remember everybody will only fit in a /24, right? If you had a /25, it wouldn't fit anymore. We all kind of use /24 as the natural unit of organization of our devices. Once things start getting to be too many to fit in a /24, most of us don't switch to a /16. Most of us will just start using more than one /24. And I think it is related to this magic of Dunbar's number. Now, moving below that line, I'm being a little bit, the numbers line up. But of course, if you have a large enterprise, it's extremely unlikely that you have everybody in a single /16. Although, if you buy one of the fancy distributed DHCP servers, you might have a central DHCP system that's laying out or handing out a specific IP address to each of the people in your company in a single /16, for example. In the intermediate levels, you might have a confederation of different DHCP servers that are each one in a different office that's roughly 150 people, and maybe they each have their own /24. And then I decided, okay, what if we look at the growth of the internet? What happened as the internet grew through these various different phases? And I found some really interesting stuff. The very first internet, once they grew beyond one node, was in 1969. They connected 4 universities together, exactly 4 nodes. So that was, the household equivalent. When they added the East Coast, it started growing to a few more nodes. It then took quite a while before we grew up to the point where we hit Dunbar's number of nodes. And I found it extremely fascinating. The only time in history that the internet has shrunk is shortly after it grew past Dunbar's number. And people apparently couldn't get along anymore. And eventually the military split off in one direction. And the university research network spent off in another direction and got it down below 150 nodes again. Almost exactly the same time, the internet was too big to fit in a single etc. host file that people can coordinate informally. They had to come up with some sort of formal mechanism for getting everybody's host names registered. And that's when they started deploying DNS. I just find it, maybe it's just a coincidence, but I found it really interesting that DNS started getting rolled out right as we crossed over Dunbar's number. Now, it took us quite a bit longer before other things started happening. Around 15K, we got SNMP because it was getting too hard to manage the number of routers. How many routers were there with 15,000 nodes on the internet? I wonder if there was maybe 150. We also got the first introduction of packet filtering where people decided they didn't necessarily want every single node talking to every single node. And it actually took up until about 60K devices before the Morris worm showed up and infected 6,000 of those 60,000 devices. And I find that really interesting. I think it sort of says, if you've got a network of 60,000 unprotected nodes all talking to each other, you'll spontaneously produce something like the Morris worm. So there are these different levels where, now the panopticon has gotten so big that infections spontaneously create themselves. Now, obviously, the Morris worm didn't completely spontaneously create itself. Some human did it, but you only needed one person to do it and ruin everything for everybody. Let's draw that as a graph because I have a few more things to show on the internet graph. But this is the basic growth of the IPv4 internet over time as measured by the number of host names in DNS, which is not a perfect measurement for kind of obvious reasons, but it tells us something about the growth rate. And so you can see so it starts off as basically a classic S curve, which I'm going to talk more about in a few minutes. For people who aren't familiar with S curves, the truth of growth is that it's very rarely actually exponential because exponential growth goes on forever. So what happens is you sort of get the appearance of exponentially increasing growth, but eventually it approaches an asymptote and that causes it to slow down again. IPv4 didn't exactly do that. It kind of shot up really fast and then whacked into a wall around 1 billion nodes in DNS. Now, If this was an in-person talk, I'd probably stop and ask the audience, hey, why do you think it whacked into a limit of at 1 billion? I think I'll ruin the surprise for you. I think it's because IPv4 has a limit of 4 billion devices, and most of them are client devices. And so about 1 billion host names is about reasonable for the number of servers you might want, or named servers you might want to be able to connect to. And of course, this doesn't say anything about the number of people behind those servers. Let's map that into a logarithmic y-axis, which makes it a little more interesting to look at. Now, what you should know about a logarithmic chart, if the y-axis is a log axis, then a straight line, a diagonal line, means that you have a constant exponential increase in the value. So anything that curves sort of downward compared to a straight angled line is slower than exponential growth, which is what we expect, right? So it starts off kind of exponential in the early days. You can see that dip from several hundred nodes back down to 45 nodes the one time the internet shrunk when ARPA and MilNet split up. You can see DNS getting rolled out around the time of Dunbar's number. And then we sort of have these clusters. Now, that could be just my own sampling bias because I looked for events that happened on the internet and I found events that happened on the internet. Nobody should be too surprised by that. But nevertheless, I find these little clumps were kind of interesting, right? So in the less than 1,000 range, we needed DNS to keep track of things. As we started getting into the tens to 100,000 range, we suddenly needed management for our routers. We suddenly needed packet filters. The basic packet filters obviously weren't enough because the Morris worm appeared only a year later. Incidentally, someone invented the first IP-IP tunnel for multicast, which amusingly, they needed to route multicast between different networks because nobody could coordinate how to make multicast work over the entire internet around 60K nodes. To this day, multicast does not work over the entire internet, but I was amused to find out that IP-IP tunnels were invented for multicast purposes back in 1988. 1989, the first connection tracking firewall was invented. Now, connection tracking firewalls, for those who aren't familiar, are necessary in order to make it so that outgoing connections can work and the return packets for those outgoing connections can come back, but people can't initiate connections into your device. Now, I don't know too much about how these events happen, but the fact that the Morris worm was in 1988 and the connection tracking firewalls were in 1999 is probably not a complete coincidence. I think those might have been invented as a response to things like the Morris worm suddenly occurring. Jumping up to the next few orders of magnitude, NAT was not invented until about 2.2 million devices, which is kind of interesting. Also, during the same year, the IP-NG, which eventually became IPv6 working group, was formulated. I think those two things are probably also related. I don't know if the two people were talking to each other, but as they needed to invent NAT in order to preserve IP addresses and protect networks from each other, somebody else said like, hey, hold on a second. We shouldn't need to do NAT. NAT is disgusting. We better solve this problem now because the internet happens to be growing very fast. You can see that it's growing exponentially because this line looks kind of exponential to me. The next year, interestingly, we got SSH. So encryption started showing up. And the year after that, Microsoft joined the team, decided the internet wasn't such a waste of time after all. And we got two important things in the same year. One of them was the ping of death, which could crash a Windows machine with a single packet. And the other one was the very first VPN, which I was surprised to learn from my coworker the other day. And I confirmed this by reading Wikipedia. The very first VPN was Microsoft PPTP, which ran PPP over internet packets and then encrypted those packets. So cryptography suddenly started catching on around 1995. And this was, of course, the beginning of the dot-com boom. But before we got to millions of nodes on the internet, nobody really thought we needed to encrypt things. I was rereading the TCP, the original TCP RFCs, and the military thought they could get away with just having a few packets in the header that said how sensitive your packet was, whether it's top secret or what. That was what the type of service header was supposed to be for. They weren't encrypting it. They were just like, oh, well, you shouldn't look at this. It's too secret for you. And I found that, obviously at very small sizes, maybe that makes sense. When you start getting to millions of nodes, apparently it stopped making sense. Also around 1995, I remember getting kicked off my local university's network when I was in high school because I was accused of breaking into their machines, which I wasn't. But they used RSH, which had giant security holes. People managed to break into lots of machines using RSH. SSH appeared the same year. So it was sort of an internet-wide phenomenon that encryption suddenly became necessary. Moving up another couple of order of magnitudes, in 2003 or so, we had the blaster worm, which was interesting because it infected lots and lots and lots of Windows machines, even though they were behind NAT and firewalls. And so in theory, there was no way for them to get in from the internet. But because networks were getting bigger and the internet was so big, the type of threats had increased again in complexity. So somebody invented a worm that can infect one machine behind your firewall. Once it did, it infected all the machines behind your firewall. Windows XP Service Pack, I forget, 2 or 3, actually finally turned on the firewall by default that same year because of the blaster worm and similar attacks. So that was the, as far as I know, first time a mainstream operating system turned on a firewall by default, preventing connections to that machine, not trusting an external firewall on the network. And then about 5 years later, the first mention of zero trust happened. There was a Forrester report talking about a zero trust architecture in 2009. Also, the Google Aurora attacks happened. I don't know too much about the Google Aurora attacks, but Google, according to Wikipedia again, was about 20,000 employees at the time. Now, interestingly, I talked to some security researchers a couple of years ago, and they told me that nowadays, tech companies estimate that you have roughly one government spy that is employed by your company for every 10,000 employees or so. So there's something magical probably about the 10 or 20,000 employee level that makes it so you can no longer trust even your employees inside your own company. You have to create a security system that keeps them from attacking each other, even though you've given them credentials that allow them to do that, right? So zero trust and Google Aurora occurring in the same year is kind of meaningful to me. I don't know if that's because of the size of the internet. I think maybe the internet became interesting to governments to actually think seriously about attacking when it was up to around this 700 million mark. And of course, not so many years later, we've had election interference and so on. Foreign governments everywhere have decided that it is actually kind of interesting to attack people on the internet now that there are so many people on the internet. It just was not interesting when there were only 10,000 people on the internet, right? You don't train spies in how to attack people when there's so little on it. So as the internet grew, things got more and more complicated. When you go up to 150, we all agree like almost nothing too complicated is necessary, right? You can have a network with no security and all the nodes connected to all the other nodes. Once you get bigger than that, there are a few different ways to organize it. So the military chooses this method, which is hierarchical. It has a lot of flaws. I'm not going to go into how many flaws the hierarchical system has, but you can tell the internet doesn't work like that. I decided to search for like internet architecture diagrams. And here's a few random samples that I found. There's this one. I don't know what this is, but it looks cool. There's this one, which shows the undersea cables that connect the internet in various different places. And one thing you can see, it's obviously not a hierarchy. It's obviously not a fully connected mesh. It's somewhere in between. That theme shows up over and over again, right? Here's another picture of an internet architecture that I found on the internet. I think it's pretty accurate. I don't know what it means. This is one of the best diagrams I've actually ever seen that compares different types of network topologies. Just to summarize them, Amazon has got the sort of perfect hierarchy shape there. That's also called a spanning tree. Google, amusingly, I don't know how many people have noticed this about the diagram, but it's actually also a hierarchy. It's just that it's super confused because they jumbled all the nodes around, which is exactly what it feels like to work at Google. But it's a hierarchy also. Facebook, it's not a fully connected mesh, but you can see that it is weirdly connected. It's a pretty good model of how Facebook actually works. Microsoft runs exactly like the US government. Apple is a centralized control, so it kind of reminds me of a software-defined network with a single control node, and then everybody else takes instructions from that. All of these things are different forms of government in humans, but also different ways of organizing a network, right? One of the things that doesn't show up in any of those diagrams is this, the fully connected mesh, because it only works when you have a small number of nodes. This is also how, when we started designing IPv6, how we thought it should work. IPv6 eliminates the need for NAT and theoretically eliminates the need for firewalls. So you should be able to connect every node to any other node. And my claim is that this was a bad idea. And that, of course, leads to my joke, how is IPv6 like string theory? They both have taken decades and have not paid off. Here's a picture of IPv6 adoption. This diagram came from something called, is 28% deployment really the limit? The answer is no, according to Betteridge. And it's because it's another S-curve. So he tried to map an S-curve onto the adoption curve of IPv6. The reason it doesn't really work that way, we have to zoom in here a little bit. The S-curve is actually made up of a whole bunch of little S-curves. So what you see is like a slow adoption for a while, then it jumps, and then slow adoption for a while, then it jumps, and so on. And what that is a whole bunch of individual networks turning on IPv6 one by one. So trying to predict what's going to happen based on this part of the graph is kind of fake, because you don't know when the networks are going to start adopting, and you don't know when a giant network is going to adopt. It's very unlikely that it's going to continue to follow this curve just based on a mathematical model. Here's another picture of the same thing. So there's math behind these multiple S-curves. For example, the COVID-19 spread, in this case in Switzerland, has the same sort of thing. So you can see that there's an event that causes the first spread, then it flattens out for a while, and then there's an event that causes the second spread. This happens all the time in exponential adoption. What do you do about the fact that networks sort of expand in leaps and bounds? Like, what is IPv6? What will make it catch on? What are the network attributes that you need in order to be a successful network, right? That brings us to Postels Law. I imagine most of you have heard of it. TCP implementation should follow a general principle of robustness. Be conservative in what you do and be liberal in what you accept from others. He never called it a law because he was being conservative in what he does. He actually called it a principle of robustness. Somebody else calls it a law. I'll rename it to Postels' suggestion because enough people disagree with it and it's not really a law. The actual law, in my words, is that the only internet that happens will be the one that follows Postels' law. What I mean by that is the internet fundamentally is a connection of other networks to each other, right? All you need is one goofball to connect your network into the internet, and now your network is connected to the internet. So the truth is, all of us are connected to the IPv4 network, and all of us are connected to the IPv6 network because those two networks got connected together by a series of goofballs over time. So if we go through enough gateways, we can connect from IPv4 to IPv6 and vice versa. The attitude of IPv4 when it was invented was like this, right? This is a diagram from who knows when, where they were showing how you can connect CompuServe and FidoNet and BitNet, and the internet was the thing that lets you tie all those things together. IPv6's attitude is different. IPv6 is it wants to be the one true network and you can eliminate all the other stuff. But because of all this stuff I just explained about how network architectures work, I don't think that architecture is going to fly. I think that's why we're not getting value from IPv6, because we keep thinking it needs to be the one network to rule them all. When the truth is, it just needs to connect other networks to each other, which it's already doing, right? So what happens, when is the time that we can actually extract the most value from the internet? And the answer is, I don't know, and I run out of time. So thank you very much.